All right, so I have posted office hours. I didn't post them until after they actually started this morning. But for the rest of the week, and in case you didn't see the post, I will be outside the classroom right after class. If you haven't, you have until the end of, well, sorry, if you haven't, you should read my comments about the exam. So not the specific comments I wrote on your exam, but the general comments about sort of how things went. The average was 72 something, 72 point something. Just about maybe a hair lower than I'd like, but it's not a disaster or anything. A lot of people did really well. If you did, like I said, congratulations. I've talked to quite a few of you, so I can make some general comments. One is it's one exam on one day. It's fairly imprecise. I mean, like I would guess we could ask a related set of questions. I could give an exam 1A today, a related set of questions, and everybody would probably score within about 10 points of where they did, which is a pretty big range, right? You guys think about it. And I think grades get used way as if they're way too precise a measure. So you know, think about what you're doing with grades. Obviously, they're they stick or carrot. If you think about sticking to carrot motivation, right? You guys, I think of them as a carrot. You guys probably think of them as a stick, whatever. But the way grades really ought to work is, you know, all the careless mistakes, all the lucky breaks, all that ought to even out over the course of your college career. And hopefully your GPA at the end sort of represents how well you performed in class here. You know, one exam is going to have a really wide play. So more important for what you take from that exam should be like, how is your preparation going, right? Like, and that's why I say, like, if you're in the 80s or above, certainly maybe even 75, like if it's 75, you can see a couple of things that you're like, oh wow, I knew that, and I just froze, or I misread the question, or whatever, then you're probably doing okay. Like, you can think, I've had a conversation with a few of you who are like, yeah, I didn't study before the test until like a couple of days before the test. We say this in organic all the time. Like, no kidding, you need to be doing some organic chemistry all the time. Like drawing molecules, I talk about it like a language. It's more like Cyrillic than it is Spanish, right? For those of you who are native English speakers, right? The letters, the symbols are different than the letters you're used to. So you really need to practice that. It's very easy for people who are not used to drawing molecules to screw up drawing molecules. And in this class, like what I'm going to look at is the molecules you draw. Like I often get it. And I try to discourage you from doing this. Like I ask a question. And like one of the bonuses that azulene, like you could have drawn a single resonance structure, put no words down, and I'd have given you it. Right? So most people fill that space with English. And you're all good writers, right? But it's not correct. So anyway, you know, if you look at it and you're like, wow, I didn't really study that much, then, well, there you go. That's an obvious thing to fix. I think generally speaking, like if you're only studying in groups, do some individual studying, right? You don't take the exam in groups. So you need to study like you're going to take the exam. At the same time, having another, I've talked to a bunch of you about this, like having somebody else sort of look at what you're doing and tell you if it's right or wrong can really be useful. So if nobody's doing that, if you're not talking to anyone else, you're never going to Chem Center, you don't have a tutor, you don't talk to a TA, you don't come see me, you don't study with anyone in here, or another class, could be somebody in one of the sections. You ought to do that, right? You work a problem, they work a problem, you exchange papers, you grade each other. So every year I see students who are right there, right? Like you write an answer that looks like a decent answer. It's a real molecule, you don't have 5 bonds, you know, it's actual atoms. But it's not quite right. Then you look at the key and you're like, oh yeah, I get that, I see that, right? The key makes sense. I see how, and you think I got it. I wrote an almost right answer down and then I read the key and understood it. Reading the key and understanding it is that's way past where you were at the start of Orgo 1. way past where you were in August when you started maybe in here. Not where we expect you to get, right? So a lot of your pre-med, it'd be like, you know, are you a good doctor if you look at the autopsy and you're like, oh yeah, see what happened. I got that. That was fun. That was actually, you guys should laugh at that. All right, so you've got to come up with the answer, like the complete answer in its entirety. And that is the last step to understand. And it's a big step, but it's one that I think a lot of you are pretty close to. So push yourself past, and then once you've done, same thing, if you've done sports or music or anything like that, like, you know, you do one thing right. Like I hit a golf ball right once, and then I'm like, I'm a golfer. I can just stop practicing, right? So that doesn't work. Like do it right once, and then do it a few more times, right? And then the other thing is like the silly mistake, the stupid mistake, the careless mistake. One, you're going to make those, even when you're a doctor. That's why there's malpractice insurance. But you're certainly going to make them in here. That's why I don't expect 100 for an A, right? You're gonna make some mistakes. Then I guess but try to slow yourself down enough that you can read the question, think about the question, double check your work. Checking is always dicey. I saw it a couple of times on this exam where someone had a correct answer written down and talked themselves out of it, erased it, scratched it out, said something wrong. I don't give you guys credit for that, but I feel for you, like, because I've done that. Generally speaking, my advice on correcting stuff when you go back to look at it is only correct it if you absolutely know what the answer is. Right? If you just look at it and you're like, I think that's wrong. Why do you think it's wrong? You know, is it because a lot of times it can be self-doubt. Like, I think that's wrong because I wrote the answer and I'm going to bet against myself. I don't think that's right. Like, don't change your answer for that. Only change your answer if you know what the answer is you want to put there. Right? So if the question is 2 + 2 and you've written 5 and you're like, oh no, I know the answer is 4, change your answer. If it's an integral and you're really not sure what the answer is, but when you had time to sit there and actually carefully work it, you came up with an answer, stick with it. It might be wrong, right? But if you don't know if you don't know for sure what the answer is, changing it, you're just likely to be wrong. You may as well go with your gut. What else was there? I think that was it. So again, if you want to talk about the exams, your exam, I guess I should say, not plural. You don't get to talk about everybody else's exam. But if you want to talk about the exam, I'm available this week. If you are considering dropping, tonight is the deadline. Check with the registrar. I am fairly sure it's midnight and you can do it by when. Don't drop just because it's 11:55 and you're panicked or something. Your roommate got in your head or whatever. But do seriously, if your score is below 60 for sure, you either need to identify something you're doing wrong that you can fix. And that might be a little more review. That might be more effort. It might be, I need to review these topics. I need to stop studying with this group, or I need to start studying with this other group. Like something concrete that you can change a little bit. The higher your score is, the less you need to change what you're doing. But I would doubt anybody in here is like there are people made in the hundreds, like there were bonus points, right? Two scores at 100 or above. And so even to those folks, I would say, like, think about what you got. Like, did I do the math? Oh, check your math also. I graded these really fast to get them back to you so you had time before the drop deadline. If I've added something wrong, so do check the math, check the key. I'm happy to talk to you about. I don't like the policy of, if you come to me for a correction, I'm going to regrade the whole thing. My experience with teachers who do that, they're going to find something to take off. If I have screwed up and taken points away I shouldn't have, I'm happy to talk to you about that. If I've taken points away from you and I'm happy with it, I'm also happy to tell you why, right? Like, I should be able to look in the eye and tell you why you missed those whatever points. Any questions about exam 1 before we get started?
For the next time, so this time we have like one practice pass exam, right? Is it okay for next time we have like two?
I'll produce more. I'm not
Yeah.
writing separate exam. I'm not gonna write 8 exams. for
Yeah,
one
yeah, I
exam.
know.
I give, the old exams I give are old exams I've given, so I wrote them at some point in the past. My sense is the material we're doing next time, there'll be more old exams.
Okay.
And I'm gonna hold one of those back. Because I've told a few other people, there's again, I'm a nervous public speaker. I think that's why I like the math so much. I may never go with it. Might start wearing dark glasses. I don't think exam 2 will be before the W deadline. So, right, there's this other drop deadline that's a withdraw deadline. You guys should not be scared of the, like, most universities have W's. I have a W on my transcript. Lots of people, you probably had people cut into you before. If people have cut into you before, likely they had W's on their transcript. So I'm not trying to encourage people to W, but if you're kind of in the middle and you're like, maybe I'll drop, maybe I won't, and I want to stick around, you probably aren't going to get an actual other grade before then. So I am going to try to produce like I said, I think I'm going to have multiple old exams. And I'll try to give one that you could take as a practice. And so like if you made a 57 on this exam and you take that practice exam and you make a 95, well, cool, you should stick around. If you made a 57 and you take the practice exam and you make a 34, then probably you should not stick around. And if you make another 57, point is, those old exams are useful problems. That raises another point. You guys should not be trying to predict what I'll ask. There's no contract that if I talk about something here, it has to be on the exam, even if I talk a lot about it. For me to ask you everything I talk about over a month, right? The exam would need to be like a month long. So don't try to guess what I'm going to do. Don't think about format. Don't think, in fact, about these questions as being from me or from the book. You're going to encounter problems in life that don't look anything like what you've seen. A lot of what you're trying to learn here in college is, how do I break that down into a problem I understand? So, and I'm not saying that's easy, right? It would look, the exam might feel better for you if I said it'll all be homework problems. We just changed facts and data and stuff like that. There was, in fact, a homework question on the exam. So, anyway, and the 2 bonuses, also the bonuses will not, I do not promise to make those old bonuses, but it happens. That was mostly laziness. So, all right. But yeah, anyway, the simple answer to your question is, yeah, I think so. I think there are more. So we're in 12 and 19. Like in principle, we're in 12, but I'm going to talk a fair amount about chapter 19 today as well. And this is roughly the interconversion of alcohols and carbonyls. Okay, so last time we did oxidation number. Let's just do. So let's do this conversion. Is this, first of all, what's the name of the compound on the left? One butyl. So there's 4 carbons. 1, 2, 3, 4. The OH is by definition on the 1 carbon. It could be here. There's a 2 butanol. And then there's a third butanol, which is actually not a high effect water. What's the name of the carboxylic acid? Butyric acid, butanoic acid. Either one of those. Butyric acid is actually the principal component of foot odor. Body odor. If you ever open a bottle of this in a closed space, you can clear it out quick. All right, things you don't need to know. That won't be on the test. So going left to right, is this an oxidation, a reduction, or nitrogen? So in oxidation, the methyls, right? These two methyls don't change anything, and nothing in the bonding of those two methyls changes. So that methyl carbon is neither oxidized nor reduced. Same thing for the two CH2s that are just bonded to other CH2s and other carbons. So the only one of these that changes, the only carbon that changes, is that one. And that actually, like in the reactions that we're going to see that carry this out, if you made this carbon a C13, that C13 would be entirely right there, right? It's not like that carbon gets oxidized and that one gets reduced. So the functional group starts on one carbon and that functional group stays on that carbon. You do the oxidation number over here. All right, so, all right, we have, I might have even done this one in class. So just a reminder, it's been 5 days. I didn't, dropping balls and whatnot. I didn't manage to actually upload Wednesday's class until this morning and put up the problems. There are now problems from Wednesday's class. I'll get problems from this class up sooner than that. So you may not remember, but we did this in class. The way to calculate an oxidation number is basically use the same procedure you use for formal charge, but don't share the electrons equally, right? When we do formal charge, we say that OH bond, the electrons are equally shared between oxygen and hydrogen. And again, that's formal charge is just bookkeeping, it's accounting. This is slightly more accurate. Okay, so we're going to say that the electrons are not shared equally unless the two atoms have equal electronegativity. And the only way to do that is to have the two atoms be identical. But as a short, basically you can take these in an organic in most organic molecules, the hydrogen's never going to get the electrons. And the O is always going to get the electron. So again, that is not an absolute rule. We're going to actually see a molecule today where that's not the way we would calculate it. But if the things are bonded to carbon, the H is never going to get the electron, the O always will. So we can redraw this. The two H's go away empty-handed, so they're just protons. The carbon gets both electrons in those bonds. The O goes away with the electrons. The two carbons split it evenly. And so the oxidation number for this carbon is the valence electrons minus the electrons that you actually see. So this winds up being, all right, 4, which is the number of valence electrons for the carbon, minus 5. All right, so the carbon here, again, the carbon has a full octet. These shared electrons, the carbon actually experiences that as having those electrons. So that carbon's neutral, it's happy, it's got a full octet. But by the bookkeeping of oxidation number, it's only got 5 electrons. So 4 valence electrons minus 5 is minus 1. So everybody do the oxidation number. You all said it was an oxidation. So good. Now do the oxidation number for the carboxylic acid. Anybody got a number? Got a +3. See some shakes, some affirmatives. All right, so let's go through that. Carbon is now bonded to an OH, double bonded to another O, and then there's a C. So we're going to break those. The OH is going to take its two. Carbonyl oxygen, the sp2 oxygen, is going to take all four of these. And the C's remain splitting them evenly. And so this is going to be 4 valence electrons minus 1. That's plus 3. Again, that carbon is not a plus 3 charge, right? So you're going to see molecules in the world that have a plus 3 charge. You'll see a lot of iron that's plus 3. This carbon is neutral. We're just thinking about like how is it sharing its electrons? Yeah. That all 4 of these come from those 4 electrons. We're not counting the lone. I'm not putting lone pairs on here at all. Right. So yeah, these 4 electrons that I'm saying go with the oxygen come from the double bond. All right. So minus 1 to plus 3. All right, so if the oxidation number increases, we call that an oxidation. If the oxidation number decreases, we call that a reduction. Right, so if we went from the carboxylic acid to the alcohol, that would be going from plus 3 to minus 1. That'd be a decrease in the oxidation number, and we would call that a reduction. And this makes a little sense. If you remember that oxidation is formally, right, oxidation is defined as loss of electrons, right? So if the charge goes up, quotes around charge here, right? If the carbon actually went from a charge of minus 1 to plus 3, that would be a loss of 4 electrons. We would definitely call that an oxidation. So this is just sort of a way to keep tabs on if all the bonds are covalent, the carbon really hasn't gained or lost any electrons. So reduction then is gain of electrons. All right, and like I said last time, you can also sort of shorthand this by just looking at how many heteroatoms. So again, if you don't remember that term from Orgo 1, a heteroatom is a non-carbon or hydrogen. So how many heteroatoms are bonded to the carbon? Well, on the left, we got 1 heteroatom bonded to the carbon. On the right, we have 3. All right, so if you add heteroatoms, basically we're replacing H with O, which is why we symbolize oxidation and reduction this way in organic chemistry. You won't see this a lot with things other than carbon-based molecules. Right? And so you can sort of try to remember it. An oxidation, bracket O, is addition of oxygen. Could also be addition of nitrogen, or chlorines, or bromines, or sulfurs, or whatever else you like. And a decrease in oxidation number is usually associated with a gain of hydrogen. So when we hydrogenate an alkene, take a carbon-carbon pi bond, reduce it to, add an H to each carbon, break the pi bond, that is a reduction. Don't get too carried away with that. But, again, we're talking about exams. It's entirely possible on exam 2, I'll ask you, draw some molecules like that and ask you if this is an oxidation or reduction. Maybe you put that aside, you're not real sure. I've called 1 minute left, and you look at it, and honestly, at that point, it's 33% chance, right? It's either an oxidation or reduction or neither. Don't leave that blank. 33% chance is that's better odds than you're going to get for most things in life. Put an answer down. But you probably don't have time to go in and do a bunch of math and redraw molecules and all that. Look at the heteroatoms, and you might be able to decide from that. Make sense? I mean, I'm not trying to teach you how to game my exams. Doing well on my exams it's really important in here right now. Means jack after you leave here, right? I don't write the exams for you in life. Knowing if something is an oxidation or a reduction for some of you in here will actually be important. So figure out how to do that. All right. So that's how to do oxidation number. Now let's talk about how we actually do an oxidation or a reduction. Look through your notes, think about this. What is the reagent we would use to do this reaction? And then going left to right is an oxidation or a reduction. And if you want, identify the functional groups in the molecule. If you want, like, trying to emphasize all this is voluntary. Anybody find the reagent yet? One of those. Yeah, so this one is going to be lithium aluminum hydride. And this is one that this pretty much comes down to memorization. I try not to make you get, I try to minimize the memorization of this class, but it's organic chemistry. You're going to memorize some. So your first answer was NaBH4 or LiAlH4. All right, those are two different reagents. Lithium aluminum hydride is the stronger of the two. Okay, so let's put that answer as a question. Lithium aluminum hydride or sodium borohydride? The answer is this is the strongest and borohydride is the weakest. So another point I'll make here, not to frighten you or anything, just to maybe hopefully tone down any complaints. There are dozens, if not hundreds, of hydride reducing agents. All right, I can find all sorts of molecules with an H in there that reacts like an H minus. So there are hydride reducing agents that are weaker than borohydride. We will probably talk about that when we talk about amines in chapter 22 or 3 or 4, something up there. There aren't many stronger than lithium aluminum hydride. There are some, but you would rarely use them in an organic lab because lithium aluminum hydride will basically reduce any carbonyl derivative. The book's going to get into some crap about like it won't reduce carboxylic acids that well, and that's fine. Some of the instructors really like you. There is another reagent that's just called BH3, which does that. Basically, I want you to learn these two. All right, lithium aluminum hydride is pretty much going to reduce any carbonyl functional group down to the alcohol. All right, we'll talk about how it does that here in a minute. Borohydride is only going to reduce aldehydes and ketones. All right, so an aldehyde or a ketone and those are the two functional groups, the carbonyl functional groups. Aldehyde and ketone, and aldehyde is a carbonyl that's got an H on it. Ketone is a carbonyl that's got 2 carbons attached to it. What is this functional group? Yeah, I should point at it more clearly, right? That's an aromatic ring, that's an alkene, that's an ester. An ester is a carboxylic acid derivative. So carboxylic acid, right? We did that over here. Carbonyl bonded to an OH. You can react carboxylic acids. We're going to see this in chapter 20, I think. You can replace the H with carbons, and that gets you an ester. You can replace the OH with nitrogen stuff, that gets you amides. You can replace it with sulfurs, that gets you thioesters, chlorides. There's a whole bunch of, basically, that O, there are ways of turning that O into any other heteroatom. But the key is it's a heteroatom. These are harder to reduce. They're a little more stable than aldehydes and ketones. And we'll talk about why down the road. For right now, just stick it in your head. Sodium borohydride is the weakest of the two hydride reducing agents we're going to talk about. Only is going to reduce aldehydes and ketones. Lithium aluminum hydride, on the other hand, is super strong, and it will reduce basically any carbonyl derivative down to an alcohol. So let's look at how that happens. Right, so there's our polyatomic anion. The aluminum hydrogen electronegativity difference is such that the aluminum is partial positive, the H partial negative. So that negative charge resides almost fully on the 4 hydrogens. So the book presents it this way. And you can write it that way. That's actually a good way to write it. I also let people sort of think about this as just the hydride. Again, I made this point. Students are always asking me, like, why do I care about this? And this is mostly because I'm recording it. Friends of mine, many of whom hold advanced degrees in chemistry, will give me a hard time if I talk about hydrides being just naked atoms. On Earth, you don't find hydrogen by itself as a proton, H+, which we write all the time. You don't find it by itself as an anion, or even as an atom, H dot. Hydrogen in any sort of monoatomic is the word, sorry. Monoatomic state is extremely reactive. And so I keep talking about on Earth, right? Think about Earth. There's O2 in the air to react with. There's H2O in the air to react with. There's carbon dioxide in the air to react with. There's all sorts of stuff on the surface to react with. Your skin, right? If we just filled this room with protons, H pluses, we would all get protonated almost instantly. That'd be a good horror movie. If anybody who's ever in here want to write a script, there you go. Fill a room with protons. We're all good bases. So you don't generally find H plus by itself or H minus by itself. Be that as it may, these reagents react like H minus. And I'm okay, I've been okay for a semester and a half, you guys just sort of saying H plus for an acid. If you want to say H minus for a hydride reducing agent, that's fine. So I've drawn the curved arrow here. Take the red, just for this time. Take this red polyatomic anion and this ester, the curved arrows I've drawn, and draw what you get. I haven't drawn that yet, so maybe you haven't done it in the notes. Go ahead and do it now. All right. Keep all the colors the same. All right, so something about these mechanisms in general, you shouldn't be able to lose overall charge. It's sort of like resonance structures, right? I've got a -1 on the polyatomic anion. I've got a neutral up here. At the end, so everything I've drawn, there's obviously this lithium plus counterion floating around. But everything I've drawn here there's a -1 charge. So what I draw here should be -1. What happens, the 2 electrons, basically the H is going to take the two electrons it's sharing with aluminum, which is why we call it an H minus. It's actually taking these two electrons. It's a new behavior for hydrogen. In general, the way to bet when you see a hydrogen do a reaction is it's not taking the electrons, right? Didn't I said this just over here. I have counteracted myself in a single panel. All right, so you see a hydrogen in here, odds are it's going to be a proton, H plus. But there are elements that are less electronegative than hydrogen, and if the hydrogen's bonded to one of them, it will take the electrons. Okay, so this H is going to take these two electrons, and it's going to attack the carbonyl. Remember, the carbonyl has partial charges here, partial plus. You guys probably can't read that. Certainly the people at home can't read it. That carbonyl is partial plus carbon, partial minus oxygen. Draw that out. Every carbonyl you ever see or experience or encounter is polarized that way, pretty significantly. You've got the inductive effect, right? Just the way carbon and oxygen share electrons. The carbon's way less electronegative, the oxygen's more electronegative. So inductively, the oxygen's pulling them up. You've also got a resonance structure where you move the pi electrons to the oxygen. That leaves the carbon with a full positive charge, the O with a full negative. All right, so the carbonyl is very strongly polarized. So the hydrogen adds to it, and you get this atom. So hydrogen has made a carbon-hydrogen bond. We've lost the pi bond, get an O minus. The sp2 carbon there is trigonal planar, it's flat. So in the absence of any chiral influence, that hydride can come from the top, from the bottom, from the front, the back. We've made a new chiral center here. This has to be racemic, right? There's nothing in this reaction that would make this non-racemic. That would be a 0% EE. We'll talk about that down the road a little bit. So is that addition reversible? Can this molecule kick the H back out? Theoretically, every reaction is reversible. If it can go forward, it can go backwards. But practically speaking, right, for this, we've got an O minus. Well, let me ask you this. What do you think is more stable, an O minus or an H minus? O minus, O is more electronegative. So this is actually quite a bit more stable. And then here's the other thing. If the O is going to do this, right? If those electrons, if the extra electrons in the O are going to like reform the pi bond and break some other bond, what bond are they going to break?
The one between the C and the other.
Right. The one that's, you're not going to break a CC bond this way. You're not going to have O minus kick out a C minus, usually, right? An unstabilized C minus. That's not going to be good. H minus is a strong base, right? You're going to kick out a super strong base or a super strong base or a somewhat weaker base. Okay, so the blue arrows are actually what happens. This is reversible. So this is a lot of that's what you get initially. This is a huge question. You got I say you guys, students ask me a lot, and there's a lot of confusion well into graduate school. Can you ask this? Is that reaction reversible or not? The question I just asked you is what just happened reversible or not reversible? It's a really important question to answer, right? We talked a little bit about kinetic and thermodynamic products. We'll talk about that again down the road, right? If the first thing that happens is irreversible, you're going to get the kinetic product. You're going to get the first thing that happens. But if it's reversible, you might get a thermodynamic product. So now I'm saying this reaction is irreversible. The addition of H to the carbonyl is irreversible. You're never going to have an O minus make a pi bond and kick out an H minus. But this reaction, an O minus kicking out an O minus, that's reversible. You could imagine, I'm going to use a different color here. Something I'm not using a lot, just to make the thought experiment. This O minus could add in, that's a plausible thing to happen. You've got an O minus, that's a good base, a decent nucleophile. It adds to the carbonyl and it makes a base of roughly the same strength. O minus makes an O minus. Okay, so that can happen, but we get back here and then we can't go any farther. So I should also say this type of reaction all right, a nucleophile attacking a carbonyl on the carbon end, you're going to see this over and over and over in this slide. Honestly, all the organic for you who are pre-med, pre-health, biochem, bio major, pretty much all the organic chemistry you've done up for now is prepared you for what I just drew. Nucleophiles attacking carbonyls, making a C nucleophile bond, losing a carbon oxygen to pi bond. Or the reverse, the O minus kicking something out. That's how we make proteins. If you replace the carbon with a phosphorus, it's how we make nucleic acids. It's how we live. More on that later. Tease you with come back to exam 3. All right, so we've got this reversible thing here. This can go back and forth, but once we get here, it can't go back here. So we're going to end up reacting from here. And if you, sorry, I'm gonna erase my yellow, orange lines here. These two are going to give us our final product. And I come back over here to this lithium aluminum hydride or sodium borohydride. Lithium aluminum hydride is strong enough to reduce all the carbonyl compounds. We just made a carbonyl compound, right? So I put the ester in lithium aluminum hydride. The hydride hits the ester. We kick out a leaving group, and that makes an aldehyde. All right. And again, another really common question you guys ask, on when you learn a new reaction is, how do I know where to stop? And the answer is, look at the product you just drew. Right? You just drew this product for me. You said that's the product. Now think about if I had set you down with the product being the reactant and given you the same reagents, would you have said it did anything? And if the answer is yes, then it will. Right? This molecule, benzaldehyde here, does not know that it's meant to be a product. It's benzaldehyde. It reacts with lithium aluminum hydride. So however you get benzaldehyde and lithium aluminum hydride, you're going to get a reaction. I'm managing the board badly. Sorry. Forget I wrote this up. I know you can't forget that. So aluminum hydride will attack the aldehyde. And again, the book is going to make this more complicated than I'm showing it. So this trivalent aluminum, actually, finish writing down what you're writing. I see a lot of people writing. I don't want to rush through. All right, so there's a lot going on here. How many electrons does this aluminum have? Got 6. Does not have a full octet. That aluminum is formally neutral. Like if I had you sit down and go through the formal charge, aluminum has 3 valence electrons minus half of 6 bonding electrons. It's a charge of 0. But it doesn't have a full octet. So aluminum, neutral aluminum, just like neutral boron above it, neutral gallium below it, is a really powerful Lewis acid, really wants electrons. And so all these O minuses I'm showing hanging around, like that O minus, sorry, this O minus would attach to an aluminum. ultimately, it doesn't really matter. An oxygen bonded to an aluminum, an oxygen bonded to lithium behaves like an O minus. All right, so pay attention to what the formal charges on those O's are. And so the last step of this is going to be just putting some acid in, right? You got to protonate that. This is step 2. That thing at the very end is the product of step 1, right? Remember, I've got 1 and 2 here. One, I take my ester, I expose it to lithium aluminum hydride, I get a product. The 1 and the 2, when you have numbers over the reaction arrow, it tells you what order you do things in. Right? If I just have this, what I'm saying is I mix lithium aluminum hydride together with the reagent and acid. And what that will do is give me a fire. All right, lithium aluminum hydride is essentially H minus, H plus, H minus, and H plus react to make hydrogen gas and release a lot of heat, burst into flames. Exciting, I've done that a few times. Lithium aluminum hydride fires are always fun. One second. So the 1 and the 2 tell me first, I react with lithium aluminum hydride. And in here, it's a theory class, right? In the lab, it would be first, in a dry solvent, react with lithium aluminum hydride for 90 minutes, for 24 hours, followed by TLC until the starting material is gone, something, right? It would give you some sort of indication of how long does step 1 go. And then step 2 would be quench the reaction by adding protons. And again, protons can be sulfuric acid. You know, you need strong acid, neat sulfuric acid. In this case, proton can actually be like sodium bicarbonate, what we think of as a weak base, because the bases that are in there are so strong that if we bring it down to pH 8, we're actually acidifying it. Okay, so H plus just basically means take all these O minuses you see and top them off with a proton.
Does lithium not act as an acid in that?
Lithium really is a spectator ion. Like the group 1 metals in general don't really do anything, and they're so stable. So in principle, like lithium plus, sodium plus, potassium plus are Lewis acids that can coordinate things, but in general, they're so weak that they don't really participate that way. Well, there's 2. But for the 1 molecule, for that molecule, there's 2 attacks and then a proton. But there's also a proton added here. And that's kind of, when you have an ester, right, we're going to reduce the carbonyl to an alcohol. So anything here that's not a C or an H will get a reduction of this to a benzyl alcohol. 2 hydrides and a H plus. No, because once you get here, right, there's no more pi bond to attack. Yeah. Yeah. So the other way this is a reduction, like if you think about a hydrogenation where we react with H2, right, that's 2 neutral H atoms. Here, these are H minuses followed by protons, right? Same thing. This is essentially an H2 if we did them at the same time. Make sense? All right. I am going to throw on the screen the board. predict the product for that reaction. This All right, so you have to, coming on the heels, this is what I say when you shouldn't learn me with class, but you should use in a properly organized lecture, right? One thing should flow into the next. So over here, we're talking about H minus attacking carbonyls. You guys up to now have seen a lot of carbocations, positively charged carbons. Orgo 2 is going to introduce you to a fair number of carbanions, negatively charged. So if you look at the electronegativity of a Grignard, you guys have done a Grignard lab. If you guys, right, you took an alkyl halide or an aryl halide, you added it to magnesium metal, you get an electron exchange that makes this carbon magnesium bond, and this essentially reacts like that carbon is minus, magnesium is 2+, and the bromide is a minus. Like things get a lot more complicated in Orgo. Like all the fundamentals you do in Orgo 1 still apply. But like we sort of talk about bonds being covalent or ionic. And it works out that a whole lot of bonds. So for most of organic chemistry, pretty much everything over here I've drawn, the bonds are covalent. This is why a lot of people, my chemistry friends, would hate me to say, some of my chemistry friends would hate me saying, just draw H minus. Right? The aluminum hydride bond is completely covalent. There's nothing ionic about it. Hydrogen does not make ionic bonds, ever. The carbon magnesium bond is almost entirely covalent. Like really, it is a covalent bond. But I think there's a lot of value in new students learning, you need to process like, how does this molecule react? And the way it reacts is like this. Okay, it's a very powerful base. So benzene has a really low pKa, really high pKa. It's a very weak acid. So, right, if we're just going to pull this proton off, if we tried to make the same carbanion using acid-base chemistry, the pKa of this proton is about 40. Again, pK units are logarithmic. So benzene is well, let's see, it's 25 orders of magnitude less acidic than water. Right, we already know water is not acidic, particularly acidic, right? I mean, it can be deprotonated, but it takes a strong base. You drink water, it doesn't ionize, the H's hang on to oxygen. Benzene's 25 orders of magnitude less acidic than that. 25 orders of magnitude is an incredibly large number. So there's no way to make this anion by just taking that proton. Right? We have to do something. So the way we do that, and I'm not going to talk about this a lot. So we would take a halogen. You guys did this. Bromide or iodine is best. and you just treat this with magnesium. Magnesium 0. Magnesium metal. You guys did this in lab. You can also we commonly do this reaction with lithium. So if you take an alkyl halide, chloride, bromide, or iodide, treat it with lithium, you basically just do an exchange. You replace the halide with a lithium. Right, so you reverse the polarity of that bond. You guys like science fiction, right? You always hear about reversing the polarity. We're reversing the polarity. So we take a C that was partial positive and we turn it into a C that's partial negative. And they are going to react like anions. So for this original reaction over here, then the negative is going to attack the carbonyl. Trying to keep to one side of the board here. So the product of step 1 will look like this. That's the product of step 1. Phenol adds into, or whatever the organic part of the Grignard is, adds into the carbonyl. It attacks the partial positive carbon. You break the pi. The leaving group is in essence the pi bond. Those pi electrons go into the oxygen. You get an O minus. Again, that's going to be countered by the magnesium. Now, is that step reversible? It's not going to be reversible, right? We go from a super strong base, negatively charged carbon, to what we would consider in water a strong base, but in organic, it's a lot less, right? The pKa of the alcohol is probably 16 or so. So again, by like 25 orders of magnitude, that's favored. This product is favored. Step 2 then, I'm going to do colors here just to make it clear. Step 2 would be protonating that O minus. And so the pKa of this proton is 16 or so, 16, 17, 18, way, way less than 40. So the O minus that you get is a much, much weaker base than the C minus that you started with. Right, so that reaction is not reversible. So we're going to talk about Grignards a lot more. This is not the last time we'll talk about Grignards, but I wanted to get it into today's class so we can talk about it. You can start to look at it a little bit, work some problems. So, and then I wanted to end the class with beginning a discussion about oxidants. So, what reagents? You can find this in the book, you can find it in your notes. What reagent would accomplish what I've shown right here? Does anybody know? Anybody have any idea?
PCC.
PCC, we got a PCC vote? Yeah? You're gonna say PCC?
O3 DMS. Probably.
O3 DMS?
Yeah. Not the
DMS is one.
Okay.
CR2. So here's the thing. There are, I don't know if there would be 1,000 or not. 1,000 is a big number. Many hundreds of reagents will do this. All right? You guys, like I said, you guys will do this. If you were so unfortunate as to drink butanol, your body would do this. All right? Alcohol dehydrogenase, some O2, bang, you got butyric acid. Your body actually makes this. It doesn't make butyric acid from butanol. You should not drink butanol. Butanol won't kill you. You should not drink it. So butanol will have most of the same effects ethanol will have on you. It's way more toxic, and the hangover is reputed to be way, way worse. And like guaranteed, if you think, hey, I drink a lot, I don't get hungover, I'm young, healthy, vibrant, butanol will kick your ass. Right? I probably wouldn't stand up for a couple of months. So don't drink butanol. Again. Don't drink ethanol. Ethanol is a poison. I joke about it. The reason I talk about ethanol in here is probably not all of you drink, hopefully. But many of you do. You have friends who do. So I find it a pathway. I find drugs and alcohol a pathway between campus and organic chemistry. Right, if any of you have a chronic illness where you're taking drugs, like prescribed drugs, that would be a better entryway. But in your age group, it's a lot less likely than people being stupid on the weekend or Wednesday or whatever. So don't drink butanol. That is not me like joking around. Like butanol is bad for you. But unlike methanol, right? Like methanol absolutely will just like you drink methanol, you're gonna be blind or dead. Those are the two options. People have drunk butanol and survived. But it is because your body will metabolize it. Your body tends to metabolize things in 2 carbon units. So ethanol and acetate. We will break a lot of carbon-based material that we eat or drink down to acetate. And then we'll start building stuff. So the way we make fatty acids, and when I say we, I mean basically every living organism, we take acetate and polymerize it. And I hope to get to that at the end of the semester. So if you look at biomolecules out in the universe, you would think it would be random. You'd have as many odd carbon molecules as even carbon molecules, and it turns out way biased to even. So butanol, hexanol, your body can deal with it. Not well, not for long, but it can try to deal with that. Methanol, propanol, not at all. Okay, so there are a lot of ways to do this. In here, the reagents I'm going to ask you, basically, I'm going to ask you to know this. Chromium 6. What's that? This is why you should make notes. I can come in here without notes and talk about organic chemistry all day long. I try to come up with a movie. Julia Roberts was in it. You guys know who Julia Roberts is? Yeah. Thank God. She worked for a lawyer. The dude from Big Fish was in it. I'm really lost. There was somebody polluting water. Aaron Brockovich. That's what. You guys, have you heard of Aaron Brockovich? If you haven't, it's a good movie. Don't not study or go to watch it, but watch it. Chromium 6 was being pumped into groundwater. Chromium 6 is a really industrially useful chemical. It's an oxidant, right? So chromium 6, remember what I said, if something gets oxidized, something else has to get reduced. Chromium plus 6 is in a really high oxidation state. So it's looking for electrons. It will take your spare electrons. So this, butanol comes along, has some spare electrons. The chromium takes it, comes out the other end, chromium 3. Chromium 3 is not that good for you either, but in an oxygen-rich environment like we have, like it's really weird that 20% of the atmosphere is oxygen. Oxygen is wildly reactive, toxic. It's a bad molecule. All right, and we all need it. So O2 reacts with chromium 3 to go back to chromium 6. And then chromium 6 does all kinds of terrible things to the body. It's a carcinogen, it's a mutagen. And you really don't want to be drinking or eating chromium 6. And so we have to be really careful. And it's a little outdated. So it's weird that I'm using this, but it's what the textbook uses. There's also sworn. So here's the thing. Any of the oxidants in the book plus water will get you from a primary alcohol to a carboxylic acid. So the reagents that you guys were trying to come up with there was Na2Cr2O7 and sulfuric acid. This is basically chromic acid. This used to be called the Jones reagent, which I obviously was biased toward. Of all the named reactions in organic chemistry, people have stopped using the Jones. I don't know. Named reactions are BS. Like there's always some misogynistic or elitist reason that the name got attached to it. And I'm sure Jones was the same. Like Jones is a lot of men have been named Jones over the course of history. I'm sure we've done some bad stuff. So anyway, you don't have to learn that it's the Jones reagent. Is that a question? Or?
No.
Some Jones had done you bad at some point. You want to tell me about it? So what happens is the dichromate gets protonated by the sulfuric acid, breaks down into essentially like CrO3. I'm not going to ask you guys for mechanisms. It's a little, for what I'm going to tell you about, it's a little strange. I'm not going to ask you for mechanisms of chromate oxidants. You're not gonna have to reproduce that mechanism. But the way this really works, so this is chromic acid. And then what will happen here, like this chromate is very electrophilic. We're going to lose water. And the book just says this happens readily, which is true enough, but that's not a mechanism, right? Think about what I would do to you if you just wrote on your, number 2 on the exam. This happens readily. That's my mechanism. Well, I'd probably laugh. I would laugh. I would get a kick out of that. And then I'd draw a line in -12 or whatever. So you wind up getting a chromate ester. And then this essentially is just an E2 elimination. I don't like asking this mechanism because this is actually fairly complex. Remember everything I've said about elements that are below the second row? Things get weird. So here the oxygen can actually attack the chromium before the leaving group leaves or without the leaving group leaving. Like things get weird and I don't want to have you do that. But from here, you need some base. And in this case, it's going to be water, right? So an OH pops off here. And the water is just going to take this proton. The CH electrons go to make a carbonyl pi bond. And the electrons, this is the important bit. Right? The electrons in the OCR bond go to the chromium. Right? So if the carbon is oxidized, something else has to get reduced. And the thing that gets reduced is the chromium. So the chromium is going to gain electrons. And we get an outlet. And this is always going to be the case. For this class, all the alcohol, the carbonyl oxidations we're going to see will look like this. There's an oxidant in there called the SWERN. There's PCC. Seriously, there are hundreds of ways to do this reaction, and they all essentially boil down to the oxygen becomes bonded to a leaving group, and then you do an elimination where you lose a hydrogen. CH electrons make a pi bond, kick out a leaving group. Kick electrons to the leaving group. Okay, so yeah.
Yeah, so the Na2 and the Cr2, where does the Na and the other Cr go?
It's complicated. You can look at it in the book if you want. This is a giant polyatomic dianion. Protonating it causes it to fall apart. So yeah, this is the kind of principal thing. If you got to make chromic acid somehow. You can take CrO3 and add it to aqueous acid. There's a lot of ways to do this. All right, so then here's the question. Like, look at this, what I just showed in red here. So an alcohol OH attacks the chromium. That's how we start oxidation. There's no alcohol OH in that lab, right? Carbonyl. So how does this happen? I'm not gonna. It is a rhetorical question, but I'm gonna close with this, and we'll start here on language. So some big picture stuff. big picture stuff, then I'm gonna leave you with something to work on before class on Wednesday. If you have an aldehyde or a ketone, well, it doesn't really matter for a ketone. It happens, but it doesn't matter. So if you have an aldehyde, that aldehyde can form a hydrate. A hydrate is what you get by adding water across the double bond. So guys, you guys know this reaction, right? We have added water across double bonds before. So if you add water across that carbon-oxygen double bond, you get what's called a hydrate. It's a 1,1 diol, right? You've got OHs on both carbons. This thing can be oxidized. There's an H there that can be lost, so you can make the carboxylic acid. It turns out that the aldehyde, that if there is no water around, the aldehyde can't be oxidized first. Okay, so in trying to predict the product of an oxidation, there's a lot of detail. I have written, I'm looking at that like, if somebody had stepped out, did anybody step out to go to the bathroom? Like, that'd be funny if they came in right now, because that's confusing as hell. All right, so there's a lot of detail there. Here's the thing that I'm trying to get across to you. So oxidizing an alcohol. Do I go all the way to the carboxylic acid, or do I stop at the aldehyde? And the question is, if there's no water, the reaction stops at the aldehyde. Okay, so the Swern and PCC, those are the two oxidants in the book. And there are dozens of these. But if you have an oxidant that will oxidize an alcohol to an acid or to an aldehyde, if there's no water in the reaction, it's going to stop at the aldehyde. If there is water, right? So if there's water, then the aldehyde will go to the carboxylic acid. It's an either or, right? You're never going to get aldehyde. It's not like we can just oxidize for a little bit and get the aldehyde. If there's water around, you get carboxylic acid. If there's no water around, you get aldehyde. And that's true whatever the oxidant is. So then it comes down to, we can't really use sodium dichromate or chromic acid to stop at the aldehyde because it's not soluble in anything but water, right? We can't dissolve that in a dry salt. So PCC is a reagent. We'll talk about that on Wednesday. PCC is a reagent that dissolves in organic solvent. The Swern oxidation, and I'm only going to ask you guys to know those reagents. You're not going to have to know that mechanism. The Swern oxidation is a whole bunch of organic things that mix together to basically give us this box. All right. So again, I just want to run through this one more time. When you guys are considering oxidation of an alcohol, right? A primary alcohol can go to an acid or an aldehyde. The secondary alcohol can only go to a ketone. All right, so you have to lose an H. You have to lose an H. A secondary alcohol only has one H to lose, so you make a ketone. That's it. A tertiary alcohol cannot be oxidized. Right? There's no H to lose in a tertiary alcohol. So tertiary alcohol, no oxidation. Secondary alcohol, ketone. Whatever the oxidant is, secondary alcohol gets oxidized to a ketone. For a primary alcohol, like I showed here, if there's no water, you get an aldehyde. If there is water, you get a carboxylic acid. That's the summary. Now your assignment for Wednesday, where we'll start. Converting an aldehyde to the hydrate, that can be done using acid or base in water. So I want you guys to come up with that mechanism, or at least look into it. It's a really good A lot of times you guys at this point still aren't terribly comfortable with proton transfer reactions. This mechanism, if you get comfortable with these two mechanisms, you'll have proton transfer down. All right, I'm gonna wrap up and then hang around for a while if you want to talk to me. Hi, everybody.